so now that we have given complete answers to questions on stationary distribution as well as limiting distributions for every irreducible Markov chain, now we turn to the question of general Markov chains, not necessarily irreducible. What happens in that case? Well, in this module, we'll try to limit ourselves to only the issue of stationary distributions and answer questions as to existence and or uniqueness of stationary distributions for a Markov chain which is not necessarily irreducible. For an aperiodic, so we were looking at the issue of limiting distributions, existence of limiting distributions for irreducible Markov chains. So we saw that if an irreducible Markov chain which is positive recurrent, so that there is a unique stationary distribution, also happens to be aperiodic, then there is a limiting distribution which actually is unique for every initial distribution. There is a limiting distribution, and the limiting distribution is the stationary distribution. So I want to now look at diperiodic Markov chains, of course with d greater than 1. What can we say in those cases? Of course, in these cases, limiting distribution would not exist. That ergodic theorem as such would not be valid. But is there some kind of an analog? So just to repeat what I just now said, for aperiodic, irreducible, positive recurrent Markov chain, we have shown that Pxy super n converges to pi y for all xy in S, where pi is the unique stationary distribution. Of course, as a consequence, the Markov chain always has a limiting distribution pi, whatever with the initial distribution. And we do know the above does not hold if the Markov chain has period d greater than 1. So as I said, question is, what is the analog, if any, of the ergodic theorem for d-periodic when d is greater than 1? To begin with, here is a simple but very useful fact. So I call it a lemma. If you have a d-periodic irreducible Markov chain with d greater than 1, then for every xy in S, there is a unique integer r greater than or equal to 0, less than d, that r may depend on xy, such that if you tell me that Pxy n is positive, then d must divide n minus r. In other words, another way of thinking of this is that every n for which Pxy n is positive leaves a remainder r when divided by d. That r depends only on xy. So the remainder is always the same when you divide by d for any n when Pxy n is positive. That means any n for which Pxy n is positive must look like a multiple of d plus r, and that r depends on x and y. So that's basically the essence of this result. Now let's see how it goes. Because of irreducibility, there is an n tilde such that Pyx n tilde is positive. But then if Pxy n is positive, that would imply, by again Chapman-Kolmogorov equations, exactly as we've seen before, that Pxx n plus n tilde would be positive, which would mean, as always, that d divides n plus n tilde. Remember, d is the common period of all states. So therefore, so this is true for any n such that Pxy is positive. So if I take two such integers, m and n, such that both Pxy m is positive and Pxy n is positive, then by that argument d would divide both m plus n tilde and n plus n tilde. But then d must divide the difference, which is that d divides m minus n. So what have we proved? We have proved that any two integers, positive integers m and n, such that Pxy m is positive and Pxy n is positive, the difference of m and n is always divisible by d. But doesn't that mean that if you divide m by d and divide n by d, they must leave the same remainder, and that's the only way that d divide m minus n. So that actually means that there is a unique r, as we said, depending on xy, such that every n with Pxy n positive, when divided by d, leave the same remainder r. So that's the proof of the lemma. So in another way, the lemma says that for any irreducible d-periodic Markov chain with d greater than 1, Pxy n would be 0 unless n is of the form some kd plus rxy. So a non-trivial limit, if any, of Pxy n may exist only along the subsequence nk equal to kd plus r, because for every other n's which is not of the form kd plus r, Pxyn is 0, therefore no non-trivial limit can exist. So what we're going to show is that when you go along this subsequence, there is indeed a limit, and the limit is somehow connected to the stationary distribution. Suppose you have an irreducible positive recurrent Markov chain with period d greater than 1, and let pi denote its unique stationary distribution. Then for every xy in S, if you denote nk to be kd plus rxy, so now think of it as a sequence in k, as k goes to infinity, nk goes to infinity. So along that subsequence, pxy nk, limit of that as k goes to infinity exists, and the limit is related to pi by this formula that it equals d pi y. So since the proof is essentially using the algorithmic theorem for aperiodic case, I'll just give a sketch of the proof. So suppose rxy is 0. Take an xy set for which rxy is 0. So in that case, consider this chain, which is, I call it yn, which is the same chain xn, but looked at not at every time point, but time points 0, d, 2d, etc. So essentially, yn is the same as the original chain, except that I am looking at times which are multiples of d. One can easily see that yn is a Markov chain, and its transition matrix is p to the d. Okay, that is because one step of the y chain is actually d steps of the x chain. Now x chain was irreducible, but recall that or keep in mind that y need not be irreducible. In fact, it won't be irreducible. So, but note that py probability that ty belongs to d, 2d, etc. is 1, because for the y chain, for the x chain, we know that starting from y, you can come back to y in either d steps or 2d steps, etc., because pyyn is 0 unless n is a multiple of d. So the original chain, starting from any state y, the time to return to y always would be a multiple of d. It can't be anything other than that. And also note that if ty is the first return time to y for the y chain, then t tilde y is ty by d, because one step for the y chain is d steps for the x chain. So from that you can easily see that py probability that ty tilde has to be ty over d. So therefore ey of ty tilde is same as ey ty by d. So now let C be x in S such that Rxy is positive. You can easily show that for the y chain, C is a closed irreducible class. Remember, we said that the y chain need not be irreducible itself. So C would be a closed irreducible class for the y chain, and the y chain restricted to C is aperiodic and positive recurrent. You can easily verify that. Now you can apply the ergodic theorem for the aperiodic case to consider and conclude that for x in C and y in C, pxy nd converges to 1 over ey of ty tilde, because we are looking at the y chain. But of course, since ey ty tilde is ey of ty tilde is same as ey of ty divided by d, you end up getting that reciprocal of ey ty tilde is nothing but d times the reciprocal of ey ty, which is of course pi y. So you end up getting this for all x, y and z. So if Rxy is 0, then this is what you get. So suppose now Rxy is positive, and fix any xy with Rxy positive and write nk equal to kd plus r. Use the Markov property to deduce that the probability of going from x to y in nk many steps would be going from x to y for the first time in md plus r many steps. These are the only possible number of steps in which you can go from x to y. Taking this to be the first time that it goes to y starting from x, so m can vary from 0 to k. So now once you go to y in md plus r many steps, then you are left to go from y to y in k minus m into d many steps. So that's what the first equality gives. You writing pyy k minus m into d as akm, we have the second equality, and denote akm to be 0 is m is greater than k. So you can write this sum as an infinite sum where AKM is PYYK minus MD if M is less than or equal to K and 0 if M is greater than K. Now, by the earlier case, we know that AKM goes to d pi bar y as K goes to infinity for each M greater than or equal to 0. AKM goes to d pi y, and since AKMs are bounded by 1 in absolute value and Px probability that Ty equal to Md plus R as M varies does add up to 1 because it's the original chain is irreducible. So starting from X you are bound to go to Y, and of course you can go from X to Y only in steps of this type Md plus R. You can apply DCT to conclude. So that's basically the analog of ergodic theorem for the d periodic case. Now the limit is d pi y. That should be intuitively clear because when you take sum over each, average over n, the average over n goes to pi, but in the average over n, when you take the sum over 1 to infinity pxy super k, the only terms that can be positive are terms that appear at a distance of d from each other. So therefore, in every sum of n many pxy super k's, there will be plenty of terms which are 0, and that average goes to pi y. So when you look at only those terms which are positive and you don't want to look at the limit of that, that has to be d pi y. Just think about it and convince yourself that intuitively the limit should be d pi y. Next we look at sort of that, and we ask this question about existence and or uniqueness of stationary distribution for a general, by that I mean not necessarily irreducible Markov chain on a state space S and transition probabilities given by Pxy. Okay. What can we say about that? We know the complete answer for irreducible cases. So what if the chain is not irreducible? What can we say, at least as far as stationary distributions are concerned? Well, to get to that, let's make some easy observations first. Start with easy observations. C, a subset of S, is called a closed class if Pxy is 0 for all x in C and y not in C. It's easy to see that for C is closed if and only if for every x in C, if you look at Pxyn, sum it over y only in C, that sum is 1, whatever be n. So that really means that starting from, if C is a closed class, then starting from any state x in C, at any time point n, the Markov chain can only be inside the class C. It cannot go outside the class C. That's what I'm claiming is that's equivalent to saying that C is a closed class. You can easily convince yourself of that. But what that means is that the original MC can be restricted to a Markov chain with state space S. Now, if C is a closed class, that's a second observation, and if pi tilde is a stationary distribution for the restricted Markov chain on C, what does that mean? That means pi tilde is a probability on C, and it satisfies the condition for stationarity for the Markov chain restricted to C, which means the transition probability matrix for the restricted chain is the original transition matrix, but only considering rows and columns coming from states in C. So it's a C cross C matrix. So if you call that matrix as P tilde, then pi tilde is pi tilde into P tilde. So suppose pi tilde is a stationary distribution for this restricted chain. Now I'm going to, out of this we are going to exhibit a stationary distribution for the original chain on the state space S. So here it is. Look at the probability pi on S, which is defined as pi y equal to pi tilde y for y in C, and pi y is 0 for y not in C. So essentially you all have a probability on C, pi tilde. You extend it to a probability on S by simply defining it to be 0 on states other than those in C. You can easily see, clearly it's a probability on S, and one can easily verify that this is a stationary distribution for the original Markov chain on S. So in other words, if you have a closed class, if your Markov chain restricted to this closed class has a stationary distribution pi tilde, then with that pi tilde you can always construct a stationary distribution pi for the original chain on state space S by simply assigning mass 0 to all states other than those in C. Next, going the other way around, suppose pi is a stationary distribution on S for the original Markov chain, and suppose C is a closed class such that pi of C is positive. I call it alpha. That means the stationary distribution pi for the original state space S gives positive mass to the class C. That means it does assign positive mass to some states in C, at least one state in C. So call that mass of C under pi to be alpha, positive. Now I'm going to define a probability on C as follows, which is just pi restricted to C, but pi restricted to C would not be a probability because the sum would simply be pi C. So I divide it by pi C, that means I divide by normalize. So pi tilde y, to be more precise, is 1 over alpha times pi y for y in C. So pi tilde y is easily seen to be a probability on C, and one can easily see that if C is a closed class, then this pi tilde, which is defined to be a probability on C, will be a stationary distribution for the Markov chain restricted to C. So what do these two observations say? The second observation says that if you have a closed class, and if the Markov chain restricted to the closed class has a stationary distribution, then that gives rise to a stationary distribution for the original Markov chain. Conversely, if pi is a stationary distribution on the original state space S, which does give positive mass to the closed class C, then by normalizing, by restricting this probability to C and normalizing, you get a stationary distribution for the Markov chain restricted to C. So this sort of goes both ways. Finally, one other observation: if pi and pi tilde are distinct stationary distributions for the Markov chain, then this really says that every convex combination of pi and pi tilde, as represented by pi super alpha as alpha pi plus 1 minus alpha pi tilde, where alpha lies between 0 and 1. So for every alpha, it can be easily checked to be a stationary distribution. That you can verify simply from the matrix equation. Pi alpha p would be equal to pi alpha if both pi and pi tilde satisfy that matrix equation. That's trivial. So with these observations, now we proceed to describe the scenario as far as stationary distributions for general Markov chains are concerned. Firstly, for any general Markov chain, the state space can be decomposed into recurrent and transient states. So that's what we have written. S is SR union ST. Of course, remember that SR could be empty sometimes. Sometimes ST also could be empty. So these are both possible. Further, we already know that SR, if SR is non-empty, that is, if there are recurrent states, then the class of recurrent states can be decomposed into closed irreducible classes. This decomposition we have already seen before, as C1 union C2, etc., etc. You remember, sometimes there could be just one, the entire SR could be one single irreducible closed class. So even though I am writing C1 union C2, etc., etc., in some special cases, there may be just one C1, nothing else. The whole of SR is one single closed irreducible class. Now, we first see that if pi is a stationary distribution for a Markov chain, then first of all, pi y has to be 0 for all y in ST. Why is that so? Pi being a stationary distribution, pi y has to equal this summation over x, pi x p x y n. This is just that matrix equation written for the state y, this linear equation. But we know that if y is transient, y belongs to ST, then pxyn goes to 0 for every x in S. Whence, by dominated convergence theorem, you can easily conclude that pi y has to be 0. So what you need to do in order to use dominated convergence theorem is to see that absolute value of pi x pxyn is less than or equal to pi x, and the series pi x converges is actually equal to 1. So pi y is 0 for all y in ST. Next, pi y is also 0 for all null recurrent y in SR. So, let C be the closed irreducible class containing y. Then the Markov chain restricted to C is an irreducible null recurrent Markov chain, right? So it does not have a stationary distribution, but if pi y were positive, that would mean that pi c is also positive, because pi c would be sum of all the pi of all points in C. So if the point y in C already has positive pi mass, then pi mass of the entire C would be positive, which means pi tilde, which is 1 over alpha pi, we have seen that on C will be a stationary distribution for the Markov chain restricted to C. That's a contradiction. So that shows that for null recurrent y in SR, also pi y is 0. So what have we seen? We have seen that if pi is a stationary distribution for the Markov chain, then number one, it must give probability 0 to every transient state. Number two, it also gives mass 0 to every null recurrent state y. What's the upshot? Upshot is, if the Markov chain has only transient and or null recurrent states, that is, there are no positive recurrent states at all, then the Markov chain cannot have any stationary distribution. So, in other words, if you have a general Markov chain, not necessarily irreducible, but that chain has only transient and and or null recurrent states, there are no positive recurrent states, then such a Markov chain has no stationary distribution. So we continue. On the other hand, suppose the Markov chain has a positive recurrent state y in SR. Let C be the closed irreducible class containing y. Then of course, MC restricted to C becomes automatically an irreducible positive recurrent Markov chain. So it has a unique stationary distribution pi tilde on C. Then we have seen how to extend such a pi tilde into a probability on S by simply putting, for points outside of C, putting the pi mass to be 0. This becomes a stationary distribution for the original Markov chain on S. Now suppose I have two distinct irreducible positive recurrent classes, C0 and C1. For I equal to 0 and 1, let pi tilde I be the unique stationary distribution for the irreducible positive recurrent Markov chain obtained by restricting the original Markov chain to Ci. So you have pi tilde 0 is a stationary distribution for the irreducible positive positive recurrent Markov chain obtained by restricting the original Markov chain to C0, and similarly pi tilde 1 that you get by restricting the Markov chain to C1. So we get pi 0 and pi 1 as above, which would be extension of pi 0 tilde and pi 1 tilde, will give two stationary distribution for the original Markov chain, and of course they are distinct because pi 0 is supported entirely on C0 and pi 1 is supported entirely on C1. So they are supported on disjoint sets, so they are distinct. But then from what we have seen earlier, that last observation, that we get an infinite number of stationary distributions for the Markov chain by considering these convex combinations of pi super 0 and pi super 1. So let's therefore summarize the observations that we made so far in the form of a theorem. So a general Markov chain has either no stationary distribution, one and only one stationary distribution, an infinite number of stationary distributions. So nothing in between is possible. And this depends, which one of these cases would arise depends on which of the following contingencies hold. So no stationary distribution. That happens if there are no positive recurrent states for the Markov chain. So in that case, there are no stationary distributions. That means all states of the Markov chain are either transient or null recurrent. Some states are transient, some states are null recurrent, but there is no state which is positive recurrent. The B part, namely the Markov chain has one and only one stationary distribution, that happens when there are positive recurrent states, but there is only one and one irreducible class of positive recurrent states. So if you look at the decomposition of SR into C0, C1, C2, etc., only one of the CIs, either SR is, all of SR is one CI, one C, and all states are positive recurrent, or you have a decomposition but only one of the CI is there, the states are positive recurrent, the others have null recurrent states. So there is only one and one irreducible class of positive recurrent states. In that case, the Markov chain has a unique stationary distribution, and that stationary distribution will be supported on that unique positive recurrent class. The third contingency, namely infinite number of stationary distributions, occur in situations when there are two or more irreducible classes of positive recurrent states. That means in the decomposition of SR into C1, C2, C3, etc., etc., two of these CIs, different CIs, consist of recurrent states which are actually also positive recurrent. So in that case, the Markov chain would have infinite number of stationary distributions for each of the irreducible positive recurrent classes. The Markov chain has a unique stationary distribution supported on that class, and convex combination of these distributions give all the possible stationary distributions for the Markov chain. So that essentially summarizes the scenario as far as stationary distributions for general Markov chains are concerned. So this is basically going to be where we are going to end, but what we have seen in this module is that for a general Markov chain, as far as the issue of stationary distribution is concerned, there are three possibilities. Either the Markov chain does not have a stationary distribution, or it has one and only one stationary distribution, or it has an infinite number of stationary distributions. There is nothing in between having one and only one stationary distribution, or the other extreme is infinitely many stationary distributions. Now, when do these happen? Roughly speaking, in case there are no positive recurrent states in a Markov chain, there are no stationary distributions. If there is a positive recurrent state, then of course, if you decompose the state of all, class of all recurrent states into closed irreducible classes, then there will be some classes with positive recurrent states. Now, if there happens to be only one such class of recurrent states where the states are all positive recurrent, all other recurrent states in other classes are null recurrent, then there is one and only one stationary distribution for the whole Markov chain, and the support of that stationary distribution is that class only. On the other hand, if it so happens that there are two disjoint, distinct, closed, irreducible classes of positive recurrent states or more, in that case, there are an infinite number of stationary distributions, and the way they arise was that if for each such closed irreducible class of positive recurrent states, there is a stationary distribution which is supported on that class, and convex combination of all these distinct stationary distributions really give us the class of all possible stationary distributions for the Markov chain. So this is basically where we are going to end our discussion on Markov chains. Hopefully, whatever we have done in this series of lectures on Markov chains would give you a complete picture of Markov chains, but I have to end by saying that there are several other important issues that we have left around, which probably require further reading in case you're interested. For example, one important issue is, suppose you have an irreducible positive recurrent Markov chain. Suppose therefore you know that there is a limiting distribution, and suppose it's aperiodic. So you know that given any initial distribution, the Markov chain would have a limit in distribution. That means as n goes to infinity, the distribution of the Markov chain goes to its stationary distribution. An important question from a practical point of view is, how fast does it approach the stationary distribution or the limiting distribution? That's an important question that needs to be answered for practical purposes. And another important topic that was not covered here is that of reversible Markov chains, which somehow happens to be connected with this question about the rate at which a Markov chain converges to stationarity. These questions seem to be related. So if in case you are interested in know further about Markov chains, these are some of the things that one can probably study. So in our next series of lectures, we'll look into some other topic in stochastic processes. But as far as Markov chain is concerned, this is where we end.